Also, thanks for the introduction. My name is Kohdai Kuroiwa from the University of Waterloo, Canada. And today I'm going to talk about our recent work, every quantum health operational advantage of quantum resources beyond convexity. And as title implies, we in this work we investigated the general properties of quantum resources, a possibly non-convex framework. And then this work is joint work with the Ryuji Takagi, Gerardo Adesso, and Hede Yamasaki. And actually, a part of this the project was carried out during the quantum research workshop last year. So I'm pretty glad that I can share this work with you today. And first of all, let me briefly introduce quantum resources and the framework of quantum resource theories. The quantum properties are used in quantum information processing tasks, which are expected to show some kind of advantage over the classical counterparts. And these quantum properties are understood as some kind of resources to overcome restrictions on quantum operations. For example, in the case of entanglement, we often consider local operation, the classical communication between distant parties. And entanglement is thought as a resource to overcome this kind of restriction. And other example is the magic states, non-Gaussianity, etc. And to maximize the utility of such quantum properties, it is convenient to have a unified framework for investigating such quantum properties. And the quantum resource theories provides such a framework that in which we can systematically analyze the properties. And then in quantum resource theories, we are usually interested in the manipulation and the quantification of resources and a restricted class of operations, which we usually call free operations. And the quantum properties are supposed to be useful in the quantum information processing tasks. So our question here is in the framework of quantum resource theory, what kind of quantum properties show actual advantage in information processing? More roughly speaking, do all quantum resource states show some kind of advantage in some task? Then previously, this question has been tackled in this the convex resource theory framework. Although I'd like to talk about the possibly non-convex framework, but it is pretty convenient to see what is done in convex frameworks. Let me briefly review the previous result on this convex resource theory and the usefulness of quantum states. So here is a general framework of quantum resource theory. At the edge is the set of density operators of the quantum states. And here in this work we consider finite dimensional hybrid space H. And in the quantum resource theory, we take a subset FH of the subset FH of the set of density operators, which we usually call the set of free states. And we call quantum states that are not contained in FH the resource state or resource states. And convex resource theories refer to the quantum resource theories with convex and usually closed FH. So actually many well-known resources are covered by this framework, for example, entanglement, coherence, and magic, and etc. General properties in this framework has been analyzed in the general quantum resource theory framework through these previous works. And in particular, in this convex framework, the quantification of the amount of resource through the well-known resource measure of the robustness of a resource has been considered. Here's a definition of generalized robustness. It's intuitively quantifies how robust, literally how robust the given state rho is against some kind of mixture with the other state tau. So this is the formal definition, but this is what I just said. We consider this kind of mixture, and we are interested in the value S for which like this mixture is actually free. And like this research measure robustness is like said to be a good research measure, like for these two properties. One is like computability for some resources, like sometimes it is like SDP formulation, like in such resources like coherence, symmetry, magic. And like it has a good property of like faithfulness, which refers to the volume of robustness is equal to 0 if and only if rho is free. So in a sense, like in other words, we can check if the given state rho is somewhat resourceful or not, only by checking the value of the generalized robustness. And by using this good resource measure of generalized robustness, it was shown that in this convex framework of resourceality, like all quantum resourceful states are useful in some task, and like they chose the task of like channel discrimination to show the usefulness of every quantum resource state in this framework. And actually, like in these research, like they consider like somewhat broader the task, which is called like sub-channel discrimination. But like for the simplicity, like let me introduce this as a channel discrimination task. So here in the framework on channel discrimination, like we have like channel ensemble, the psi pi. The channel psi I will be applied to the state with probability pi. And like in this task, like we have a quantum state, and we pass the quantum state through this gadget of the channel ensemble. And some channel from the ensemble will be applied, but like we don't know which channel was applied to it. And then after getting the resulting state, like to identify which channel was applied, we perform like the quantum measurement represented by the PLPM element MI. And the goal is to maximize the success probability of the discrimination, which is formally defined like this. And in this like previous research, when maximized over the discrimination task pi psi I, and when we maximize over the like measurement strategy mi, when we consider the ratio, the success probability of the quantum state rho to success probability of all free states sigma, then like this ratio like can be written as a 1 plus robustness of rho. And recalling that like this robustness has a good property of like faithfulness, it shows that like this ratio is strictly larger than 1 if and only if rho is resourceful. And so which means like if rho is somewhat resourceful, then like for every quantum resourceful state, this ratio is larger than 1. So like success probability in the resourceful state of rho is always larger than the success probability of all the free states sigma. So like so far in the convex framework, so good, but actually like we would like to consider non-convex, possibly non-convex framework, because like not all physically motivated quantum resources can be covered by this like convex resource theory framework. Actually, like I took these slides from the like my collaborators talk back in like at a quantum research workshop last year, and then they pointed out, for example, the like set of set of Gaussian states is non-convex, like unless we consider the convex mixture. And like the set of quantum states with no discode is non-convex. And the set of quantum Markov states is non-convex, we know. And like besides that, we sometimes want to consider the setup where we have multiple type of free states. So like, for example, suppose like we have 3 kinds of free state, F1, F2, F3, then like we would like to consider the union of these 3 kinds of free states. Then after taking the union, in the case like most likely the resulting set of free state is non-convex. So considering this setup, like we cannot directly apply the previous convex framework and a new technique is needed to like tackle the problem in this like possibly non-convex framework. So the question here is like, in this setup, without convex assumption, are all quantum resources still useful in some task at all? And like in this talk, I would like to give an affirmative answer. I'd like to say yes, and I'll show yes. But like before moving on to our main result, like let me briefly like explain why convex works better previously and why it fails for non-convex. And the main technique used in convex result theory is, as you might suspect, convex optimization. And here is like the definition of generalized robustness. And in convex result theory, like this can be regarded as a convex optimization problem. And then in the case like we take the dual of this problem, and like actually it can be written like this. And in convex case, by considering some kind of like mathematical assumption, we can prove like the strong duality. So like the optimum value of this primal problem and the optimum value of this dual problem is the same by using for example, Slater's condition. And this dual problem has a clear meaning of the linear resource weakness, like when considering the like optimal solution of this problem, like the solution represents the hyperplane that separates the resource state rho from the set of traces F. And so like there's a clear connection between the generalized robustness and the linear resource weakness in this case. And this connection plays an important role in the like proof of the usefulness of resource states previously. However, okay, why it fails for non-convex? Because like it is non-convex, obviously. When FH is non-convex, then like we don't have like linear resource weakness in general. For example, like suppose that FH has its shape and suppose that like rho is located in this position, then like no hyperplane can separate the rho from FH perfectly. So like we have to deal with this problem to like tackle the problem of like usefulness of quantum states. And actually like in this work, we proposed like two ways to resolve this issue. One is like, okay, no linear weakness doesn't work. So like, why don't we consider non-linear weakness that are based on the generalized robustness? And the second approach is, okay, non-convex set of free state doesn't work. So however, like let us consider the composition of the set of free state into convex components. So like these two like approaches are like different yet kind of related. And in those two approaches, like we showed that every quantum resource state is somewhat useful in some tasks, even without the convex assumption. So yeah, I'll explain the two results one by one. First of all, like I'll explain the non-linear witness case, like advantage-based multi-copy witness. So main idea is, as I said, like let's construct a non-linear witness based on the definition, generalized robustness. So the question is like, given this like definition of like generalized robustness, now like FH is no longer convex, like it might be non-convex. In the case like, can we construct some Hermitian operator W, which acts on n copies of the input state, and that can separate the resource state rho from the set of free states FH. And can we find such kind of W and M? This is the question. And I'd like to say like, yes, if we can construct such kind of witness, yeah, like for the simplicity of the explanation, let me consider the like simplest case of one qubit case. So recall that like this is the definition of generalized robustness. We'd like to consider multi-copy witness based on the definition. So inspired by this mixture, for each fixed parameter value S, let us consider the set of quantum states ether that has this like mixture expression of rho and some pure state pi and s. And we'd like to use this set as a like hypercurve, like separating a resource state from the set of free states FH in this case. So like maybe like since the case is now when cubic, maybe like it is convenient to take the block space, and intuitively like this ether represents a quantum state which internally divides rho and the surface of the block sphere into the ratio s and 1, s to 1. And like actually, they're doing a simple computation. Like we find that like this set on the block sphere has like the 3D sphere like shape, and here like this is the block sphere projected on XY plane, and I draw like the 3 spheres corresponding to 3 different values of s, s1, s2, s3. By construction, like we can prove that when the value of s is smaller than the generalized robustness, then the resource state rho is inside the like this 3D sphere, and like the set of free state f is always outside of the this 3D sphere. Then, like by considering the block vector characterization, we can really compute the like expression of this 3D sphere in this case. And so rho is inside of this sphere, and the set of free states is outside of this sphere. So actually, like now that we have this quadratic form of the curve, we can actually construct Hermitian operator that acts on 2 copies of the quantum states, rho tensor 2 or like sigma tensor 2. And like as I said, like if S is smaller than the generalized robustness, then like this WS actually like separates the resource state rho from the set of free states F in the case. And this is what we wanted, like this is like the what we call quadratic witness in the case, possibly non-convex case. And based on this like quadratic witness we constructed, we can actually design a 2-copy channel discrimination task in the case. Now like the channel acts on 2 copies of the input state, and we can prove that like the maximum success probability with respect to rho is always larger than like success probability in sigma when maximized over all free state sigma. So which shows like the advantage of every resource state based on the quadratic witness, even in the like possibly non-convex framework. And actually, like I only talked about like the 1 qubit case, and we can extend this analysis to general d-dimensional cases. Like the discussion is a bit more complicated, so like please see our paper for more details. But like basically, idea is like we can construct a family WS and Hermitian operators, where like each WSN acts on n copies of m. And when we maximize over m, like this family works as like resource witness in this case. And based on this family of witness, we can construct a family of channel ensembles, the channel discrimination problem, where like when we maximize over m, like we can see like some kind of advantage of every quantum resource state. So like this is a result for the multi-copy witness, and let me consider like worst case advantage based on the computation. So this is motivated by the framework where we have multiple kinds of free states, like coherence in multiple bases and thermodynamics with several sum of that. And in the context of multi-product entanglement, biseparable entanglement in the case. So like all these cases, like we naturally have the decomposition of the set of free state into some convex set in the case. And when we have like this kind of convex decomposition of the set of free state, actually like this the robustness has a like meaning as a like worst case robustness with respect to each convex component. And we can actually show this relationship like as like depicted in this figure. And now like this situation is pretty good because like we have the result from the convex framework. So each convex component, we can show this kind of relationship that is like taken by the previous convex result. So now let's go because let's think about like infimum of the each component J. And since like this worst case characterization of robustness is actually equal to the generalized robustness in this like possibly non-convex framework. So this is understood as a like generalized robustness in this case has the operational meaning as a worst case advantage in this channel channel discrimination task. And like this expression shows that like every quantum resource state row has some kind of advantage of all free state sigma in FH. So in summary, like we show the usefulness of every quantum resource without convex assumption, like based on multi-copy witness and the worst case robustness. And actually, like we extended our result to the another resource measure of like weight-based resource measure. And like we also extended our results to the dynamical resources of like quantum channel and instruments. And as a future direction, like I'd like to think about like our multi-copy witness depends on the dimensions. So like, can we design the m-copy witness for constant and so that like we can extend our result to the possibly infinite dimensional case? Or like we take worst case advantage, but like, can we design another task for which we don't like necessarily take the worst case? Is there any other task? So thanks for listening and happy to take your questions. Thanks.
Questions?
Thanks for great talk. So could you explain once more about the necessity to consider the non-convexity of free state? Because in my intuition, so once we if we could prepare some free states from several FI domain, then yeah, surely naturally we can prepare some probabilistic sampling of those. So I don't know, and yeah, so I don't know the why we should consider some non-convexity and non-convex free space spaces.
Oh yeah, like they're like in nature, like the set of like the so-called like free states, like that are in nature non-convex. But like for sure, like you can take the convex hull, the convex combination of the free states if you want. But like sometimes this kind of randomness is highly resourceful in some sense, like the principle called the talk from yesterday of like concave resource theory, and in some cases like this kind of convex mixture is pretty resourceful, we could say. So that's why like I consider like this kind of non-convex framework in this research.
Okay, thank you very much.
Thanks for the question.
Thanks for your talk. In the multi-copy witness part, how can you decide how many copies are needed to find a witness?
So like it's depending on the dimension of the state you consider. So like in one qubit case, like since the dimension is 2, so like we eventually have like 2 copy witness here. And like the story is like a bit complicated in the general case, because like we actually construct a family node Hamilton operators witness. So like you basically need like the m copy weakness from m is equal to 2 to the dimension b. So to answer your question, like you basically need like b copy weakness for the dimension b.
Any more questions?
Thanks for the great talk. I guess I have two questions. The first is really quick. Discord is one of the first, I guess, non-convex resource theories.
Yeah.
Does any of your have you tried applying any of your general constructions to Discord in terms of understanding its interpretation, let's say, multi-channel, multi-state discrimination, or?
Oh yeah, like we haven't thought about it, but like that would be a great next direction, I'd say. Yeah.
The second thing is, I guess, with dynamical resource theories, especially say on channels and combs.
Yeah.
You briefly mentioned the example of Markov chains.
Yeah.
Or Markov order type resource theories. Is there a natural way of generalizing the framework that you have to some interpretation on resource theories of channels and beyond?
Yes, I would say like it is possible, like I don't know, especially for the the Markov chain case, but like as I mentioned in conclusion, like we have like some kind of extension to the like dynamical resources, so like it is highly likely possible.
Right.
Yeah.
That's something that's worth discussing. Cool, thanks.
Yeah, thanks so much.
Yeah, just also a follow-up question to that. Do you have any like ideas or candidates of resource theories that you think would be particularly benefited by your framework?
But the framework is like, for example, like the operational resource theory of non-Markov entity is like where the free state is like this quantum Markov states, and in this framework, like convex mixture was not considered by its nature. So like this non-convex framework is pretty crucial in the kind of framework. So that is one option, I guess.
Sounds very interesting. Thank you. Any more questions? Okay, then I think we'll have to move on.